Now there's another interesting set of effects that occur in materials which are conductors called eddy currents. Now an eddy current is generated whenever you have a material like a piece of metal, okay? And if there's a changing magnetic field, if you bring a magnet near it or pass it through a magnetic field, the charge, which is free to move inside a conductor, the charge feels a magnetic force. Now, if a charge is moving that way and the magnetic field is that way, it feels a force to the left, right? So if you work it out, and that diagram sort of shows you how it looks, as the field is changing, you get swirls, a swirly pattern, or that's what the word eddy comes from. You've seen eddies in like a creek or something like that. As the water flows, it creates those little swirls. You can imagine little swirls of charge, little swirls of current inside the metal that occur. Well, metal is a resistor. Aluminum is a resistor. It's not a perfect conductor. And so we're going to demonstrate what happens when you do that. Now here we have a pendulum. This is just a piece of plastic. And it swings back and forth quite happily past this magnet. The magnet is a fairly strong, permanent magnet. Good. So now let's put the aluminum in there. And let's try to predict what's going to happen. Anyone want to take a guess? What happens when I swing the aluminum through the same magnetic field? Well, as it passes through the magnetic field, the forces will cause these swirls of current. The swirls are resisted, right? I mean, aluminum is a resistor as well as a conductor, since it's not a perfect conductor. And that, if there's current with a resistor, what happens? It heats it up, right? You know that, right? If you pass a current through a resistor, it gets warmer. That's energy. So where does that energy going to come from? Whoops. What happened there? It just stops cold. So the amount of energy lost in the resistance of the metal to the eddy currents comes from the kinetic energy of the pendulum itself. So let's prove that. Let's prove that. So that there are swirls of current flowing through this disk. We can prove that. We have the same kind of aluminum, but now we've cut slits in it that prevent the currents from flowing in the circular pattern like that. You can get tiny little ones, but they can't be very big. Now we know it's the same thing, and it will eventually slow down and stop due to the small eddy currents. And it loses its energy like so. Let's go back to the plastic for a minute. Did the plastic slow down that fast? Here's the plastic. I think the plastic is just pretty much happy to keep going. So we dramatically reduced the eddy currents. Let's find another geometry. How about this ring? In this ring, the eddy currents are constrained to go around through the metal on the outside instead. So what do you predict is going to happen with this ring? Is it going to come to a dead stop the way the first one did? Well, not quite. But it slows down pretty quickly. You get just a few swings through there. If you actually want to feel this yourself, come down after class, and then you can take this big piece of metal and put it through this field here. It feels very weird. This is not a magnet, right? It doesn't stick to this. Not the way, I don't have a piece of iron here, I don't think, but certainly another magnet, you can feel how much that sticks to this thing. It's lots of force. But try this yourself. I urge you. Now, one time, when I was a graduate student, working at Fermilab in Chicago. Our experiment had a big magnet with an open air gap, what we call a field gap, about a meter big. And we wanted to measure the magnetic field inside this, like a 1 meter tall by 2 meters wide, 2 meter deep field. And it was about 2.3 Tesla, quite a strong magnetic field. And a lot of weird things happened when we were trying to measure this field. One of them is when I walked toward the magnet while it was on, I felt the knife in my pocket was practically trying to jump out and into the magnetic field. You definitely couldn't work with any credit cards or magnetic cards in your pocket there. But the weirdest thing was this. We had what's called a Hall probe for measuring the strength of the magnetic field. And we wanted to measure it right at the center of the field gap. And to do that, we just got a big bar of aluminum and then set this probe, this magnetic field probe, on top of it. And the bar of aluminum was long and narrow, like about 3 inches wide by 3 inches wide by about this high. And of course, being a slightly clumsy person at times, and I climbed into this field gap to set this thing up. As I was coming out, I knocked it with my hand. Okay, the probe fell off, but it was a pretty tough thing. That didn't matter. But I knocked over the aluminum. Now the aluminum, it just made the hair on the back of my neck stand up. Rather than just falling over like a piece of aluminum should in a gravitational field, it did this. It fell slowly, 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 and then sort of set itself down. And we said, holy, you know what? So we set it back up and kept knocking it down just to see this effect of the eddy currents flowing in this bar of aluminum made it just fall super slowly in the magnetic field. We can demonstrate an effect very closely related to that using this device again. Here we have the time-varying magnetic field in the steel rod on top here. And all we're going to do is put this loop of aluminum. It's just a little circular cylindrical sleeve of aluminum. Oh, don't leave. This is the best part. And as soon as I turn this switch on, what's going to happen? Well, it'll induce currents in this thing, right? Fortunately, I knew that was going to happen, so I was ready to catch it. Now, if you didn't believe that the first time, see it again. You could try this after class too. Also, the thing that you might want to try is to just hold this. Feels really weird. And if you let it go, flies up. Of course, as soon as people figured out that you could shoot things with with a changing magnetic field like that, we put it to very good use. One of the good uses is, I think it's called California Screaming, or at least it used to be at Disneyland, California Adventure. Have you been to this? There's a nice viewing platform where you can watch this thing. It is an electromagnetic rail launcher that launches you at something like 50 miles an hour coming out of the stall of that thing. And then the ride goes up, and it comes back, and then I think it actually slows you down as well. But that's exactly how that ride works. It's really an electromagnetic rail launcher. Now, of course, the people most interested in this are the military. And the U.S. Navy is now deploying an electromagnetic railgun. Have you heard about this? Have you seen it? Again, if you go to YouTube and put in railgun or something like that, or Navy railgun, you'll find these fantastic videos that show what the Navy's been able to do. In the next generation, or now new generation battleships that are being deployed, the railgun, and these things are nuclear powered, right, the ships. The railgun uses a lot of energy, though. When the ship wants to fire a projectile from its railgun, it uses about half of the power from the nuclear reactor on board the ship to charge a huge bank of capacitors, and then the current is dumped across the rails to shoot a projectile. The projectile is shot at Mach 8, okay? And it comes flying out of there. When it hits its target, which can be up to 400 miles away, and it's just ballistic, right? You just send this thing up, and it goes down, and if you've pointed it at the right place, it hits the intended target at Mach 8. The kinetic energy alone of the projectile is enough to destroy the target. And it's pretty devastating, and a lot of the tests that they've done are pretty impressive. You should go look at it. It's really an amazing thing that they've created. So there's no high explosives. It's not like a shell, not like a naval shell that has, when it hits the target, it explodes. It's just from the kinetic energy upon arrival that destroys the target.